set, and we will have our first problem session tomorrow at 10:30, and stick around close to noon.
We have Labor Day on Monday,
So for all our hard labor, we won't have a office hour. For my usual office hour won't start, but I'll be available after class on Tuesday. I still haven't heard from most of people about availability on Tuesday, so that's go ahead and schedule his office hours. So please send me that information. Try to do our best to accommodate everybody. All right. So last time we were talking about linear operators. Operators are maps on the vectors in Hilbert space, and linear operators satisfy the property that the map on the linear combination is the same linear combination of the map on the individual pieces. And there's an intimate relationship between linear operators and matrices. They're one and the same object, really. And so in particular, we can write, as we saw, representations of an operator, particularly on a finite dimensional Hilbert space. We'll get into the question of infinite dimensionals. It'll be very important for the study of quantum mechanics and how you deal with that mathematically. We'll get to that a little bit later. For the moment, let's just restrict our attention to finite dimensions. And if we have a finite dimensional Hilbert space, if we have an orthonormal basis for that space, as we know, we can write a resolution of the identity and use that to quickly write a representation of the operator in terms of a combination of transition operators between the basis elements weighted by these complex numbers. And those complex numbers, the array of them form a matrix. Okay, so this is a matrix representation of the operator in a basis. And these numbers are the matrix elements, the elements of the matrix. Okay? So the first index is the row and the second index is the column. And I can think about, well, there's many ways to remember or think about the matrix representation. A useful way is think about each column of the matrix is really just the vector that one obtains by operating the operator on the basis vector associated with that column, represented in the basis of interest. Okay? So this is the vector m on E1 represented with coordinates in the basis by projecting it onto all that. Is that clear? We'll see an example. Maybe a little bit more clear. It's not completely clear to you what I'm trying to say here. Right. Okay, so we talked about, basic matrix operations like the inverse and the act of the adjoint. The matrix elements of the adjoint operator are given by the complex conjugate transpose of that. And we talked about special classes of matrices or of operators. So we talked about Hermitian operators. Hermitian operators also are called self-adjoint. And we also have anti-Hermitian operators, sometimes called skew Hermitian, which satisfy that property. Yeah,
Is I times a Hermitian matrix anti-Hermitian?
always, always. So, as we said last time, we can always talk, a Hermitian operator is kind of the moral equivalent of a real number. And the anti-Hermitian operator is kind of the moral equivalent of imaginary number. And an imaginary number is I times a real number. Yeah, please.
Oh, I'm sorry, I didn't hear the question.
The question was, is every anti-Hermitian operator I, the complex number I, times a Hermitian operator?
Okay.
And the answer is yes, for this very reason, right? Because if I divide an anti-Hermitian operator by I, well then it's Hermitian. Okay. Okay, and the other important class, very important class of operators that we talked about briefly are unitary operators. Unitary operators are almost always called U. By the way, Hermitian operators are generally called H. Sometimes I'll call a Hermitian operator A. We're going to do that. So there's some kind of notation that is that we use all the time and some we don't. We almost always call unitary operator U. Sometimes we call it B, but generally we call it U. And a unitary operator is such that its inverse is its adjoint. Okay? And so that is to say, U dagger U is U dagger is the identity. And these have the important property that they preserve the inner product. That is to say, if I map every vector in a Hilbert space by this map, then whatever the inner product was before, between two vectors, stays that inner product. Okay, we proved that last time. So that's an important property to keep in mind. You might say that's really the defining property of a unitary operator from which all this other stuff follows, depending what you want to call the definition. And if we have an orthonormal basis for the space, and we define the set mu tilde I as what I get by mapping each of the EIs by this U, then this is also orthonormal. Okay? So another thing to keep in mind about unitary operators is that they can be thought about as maps that take orthonormal bases to other orthonormal bases. It's another way to think about that. So I can write U, if I like, as a transition operator that takes this basis vector to that basis vector. You can think about E tilde as the image of the vector under the map. Okay? What we said then is that if I wanted to look at a change of basis, a change of representation, so this matrix is one representation of the operator in this basis. But I can choose a different representation. It's a representation of the same operator, but just with respect to a different basis. And those two different representations are related to one another through a change of basis that is a unitary transformation. So just once again, to emphasize that fact, if I look at the, let's look at the matrix elements, so here I'm talking about a change of basis. Okay, so here's the representation in a new basis. Let me call that L tilde. Right? So if I want to find out how these matrix elements are related to these matrix elements.
Plus,
Bless you. What I do is insert a resolution of the identity my arrows look like my unity, so I'll just in here, right? And I do that with respect to the basis I now want to represent the operators. That basis is, so this is, I'll write it all out just to emphasize these facts. So we can't use I and J anymore. We gotta use different dummy indices. That's always the trick. Be very careful about that. So. And that is thus equal to sum over L and K, EI tilde EL, ELM, EK, EK, EJ tilde. Okay? So these are the matrix elements in the new basis, and these are the matrix elements in the old basis. Okay, what we call old, what we call new. This is the untilted basis, this is the tilted basis. And these things are what? Well, this is equal to the matrix element of this U. That's to say, it's the matrix element associated with the U that takes me between the old basis and the new basis. Right? And this is, as we showed last time, the adjoint in matrix. Right? So this is a unitary transformation. Okay? That takes me from this basis, this is an example of what we call a unitary transformation. All right? And similarly, we can change the representation of a vector, not just a matrix. It's in the notes. Check it out for yourself. All right. Any questions so far? All right, so far so good, pretty straightforward, I think. Let's just quickly review an example here. So a particular set of operators that you're familiar with, and just let me really do, will play an important role in lots of the physics that we'll talk about are the Pauli operators. Now, the Pauli operators are familiar in the theory of spin 1/2, but as we will see, they're kind of more, they're useful more generally than just thinking about the problem of spin. We'll see that. So what are the definitions? So if I have a spin 1/2 particle, then we know that I can form a basis for the space that describes the spin state as two possible spin states. I'll call them spin up along Z and spin down along Z, and I'll call them plus and minus for reasons that will become clearer in a moment, maybe in a few moments. Okay? So in that basis, so this is spin up along Z. And this is spin down. All right? And so, what are the operators? So, sigma x is equal to this operator. sigma y is equal to this operator. And sigma z is equal to this operator. Those are the operators written in this kind of notation. There's lots of notations that we can use to express operators, but this is one of them. Now, although I've written it with respect to this basis, this is really a basis-independent expression. Because I can change the basis quickly, but this object equals that object. It's not that it's represented by it, it's actually the same object. Okay? But we can write a representation in basis. So in that particular basis, we can write a matrix representation of these operators in this basis, right? So how do you do that? Just again to emphasize, right? So, you know, sigma x, say S prime, where S is plus or minus 1, along with this one of these guys, right? That's the matrix elements. And what do we see about those matrix elements? So if I wanted to then look at that, where I would say sigma x as a matrix, I have to do those matrix elements, right? So what you see first of all is the diagonal matrix elements. What are they? They're 0, right? Because if I look at, for example, plus, well, I put plus, I put the sandwich like that, right? Plus on that is 0. Because they're orthogonal. Clear? And plus on this is 0. Because it's orthogonal. So both of the diagonal matrix elements are 0. Is that clear? What about the off-diagonal elements? Well, I have to, let's look at, so this is 0 and minus is also 0. What about plus, that's row plus, column minus? Let's take a look. So, I put plus on this guy and minus on that guy, right? And what is that? 1. And then I put plus on that guy and minus on that guy. What is that? 0. So this matrix element is 1. It would be 2 if it was, well, okay, anyway, it's 1. And similarly, the other guy, using the same kind of thing. Okay. So that's the matrix representation of sigma x in the basis of spin up and down along Z. Okay. What about sigma y? Can you just tell me now, what its matrix representation is? Well, it looks just like this guy, except instead of 1s over here, it has these plus and minus i's. So firstly, what are its diagonal matrix elements? 0. They're 0, right? What about the off-diagonal ones? Well, one of them is I, and the other one is minus I. Which one is which? Remember, row, column. And we're doing it in this order. That's important. When you write down a matrix, it's always with respect to a particular order of the bases. You have to know what order I'm talking about. I didn't actually tell you. I'm writing this in the order plus minus. I didn't have to. We could write it any way we like, but we have to know a matrix has, when you write a matrix, you're always specifying the order in which you're specifying the elements of the basis. If you don't know what that is a priori, it's meaningless what the matrix is. Okay? So in that order, if this is, so this is column plus, this is column minus, this is, the row.
Minus I on top, right?
So, right, because it's row, column, right? So plus, minus. Okay. And what about sigma z? Let's just think about that for a second. What are the diagonal elements of this? Are they 0? Not this time, right? Because if I put plus plus here, what do I get on this guy? I get 1, and here I get 0, so that plus plus, that's 1. And for minus minus? Negative 1. And what about the off-diagonal matrix elements? They're 0 this time. So this guy is a diagonal matrix. Obviously, this is an example where, as we know, we'll talk about more this lecture, these vectors are the eigenvectors of this matrix, and or this operator, and a matrix or an operator represented in the basis of its own eigenvectors is diagonal, where the diagonal elements are the eigenvalues, and that's why I'm calling these things plus and minus, because sigma z acting on plus and minus z is plus and minus 1 times that. These are eigenvectors, and these are the eigenvalues of that operator. Yes, Steve?
I think if I'm not mistaken, in the homework we got the same things, but with halves instead of, as the coefficient instead of 1.
That's
Are they different
yeah, those are
objects?
remember that the spin operator is h bar over 2 times the sigma operator.
Okay.
Okay, and I said h bar to 1.
Okay, so, okay, yeah.
H bar's always 1.
It's not always. It's who you are. I like h bar. We'll see why. It's important to keep h bar around sometimes. Alrighty, cool. Now there's some interesting properties of the Pauli matrices, or the Pauli operators, depending on how you look at it. You could look at them as a matrix. Remember, these of course are representations. You might say these are the standard representation. When someone says, write down the Pauli matrices, they always mean these. Because the Pauli matrices are understood to be the Pauli operators represented in this basis. Okay. All right, so with that said, what are some other interesting things we could say about these matrices? Firstly, or these operators, the Pauli operators are Hermitian. For any of those indices. Is that clear? There are lots of ways to see it. If let's just to get a feel for and remind ourselves about the different kinds of manipulations we do, let's just take the adjoints of these different operators. Okay, so let's just, for that, let's look at, let's do sigma y. So that is the adjoint of that, right? And how do you take that adjoint? Well, the way you take an adjoint is you complex conjugate. So minus I goes to plus I, and then you switch the bras and the kets. That's equivalent to doing the transpose. And that, of course, is the same thing. And then it's obvious. You split the bras and the kets, and you get back. So all of them, these are all permission operators. They have another interesting property. All of them, if I look at the square of them, they just happens to be, this is a very special property of Pauli operators, they all square to the identity. You can do that in many ways. Let me do this by matrix multiplication. Sometimes it's easier. I mean, you know, this is to some degree a matter of taste. What you're more comfortable with, play around with the bras and kets or play around with the matrices. I can look at sigma y squared as being represented by the matrix multiplication of these two matrices. Right? That's one way to do it. And so plus I is minus I have 0, I get 1, get 0 times 0, 0. Go the other way, 0, 1. So this is the identity. And that's true for all of them. You can do that check. So an interesting factoid here is that not only are Pauli matrices or Pauli operators Hermitian, they're also unitary, right? Because if I look at one of these guys times its adjoint, then that is the same thing as it times itself because it's self-adjoint. And that what we said is that this is 1. So there's an interesting fact about this, that these guys, all the Pauli operators are also happen to be unitary and Hermitian at the same time. It's kind of fun. All right, let me go grab my notes, pardon me. Remind myself of where the heck I'm headed next. All right, any questions?
Isn't it fourth probably that sigma A alpha, sigma sub alpha times sigma sub beta is 0, if alpha is not equal beta?
No, that's not quite true. We'll see what that property is in a moment. There are lots of other properties of sigma matrices, and we'll see some of them today, and we'll get to some more of them later. But let's hold off on that. All right, so what I want to talk about now are just when we spend the rest of the lecture, and probably into next week, talking more about operator algebra. So, for example, one property of operators that we can do. Oh, of course, what we can talk about here is I can talk about the composition of operators. So A times B has a meaning because AB on a vector is just what I get when first I act B on the vector, that's some other vector, and then I act A on it. That's just the definition. Of course, we did that by matrix multiplication. So I can ask the question of what is the adjoint of the composition? And the answer you can easily prove, which we'll do quickly, is this. That is to say, the adjoint of the product is the product of the adjoints, but in the other order. Okay? How do we prove that? Well, let's look at this, and let's call this thing W. So A, B adjoint acting on V is the adjoint of A acting on W. And the adjoint of A acting on W is the bra, the acting the adjoint that way, by definition. Okay? No, this is all screwed up. Yeah, the adjoint should be here. Maybe it's what am I screwing up? All right. Woo. Let's start again. Okay. So I'm going to let W equal A, B on U. Is that what I want? Yeah, that's what I want. And let V equal B acting on U. Okay? So now I can say the dagger of W is U, and then the adjoint of whatever this is. That's right. Okay, you buy that? And so V is V on U, and W is A on B. So this is equal to V, A dagger. But V dagger, or V bra, is equal to U bra, V dagger, A dagger. And thus, this is equal to that. That's correct. So the adjoint of a product is the product of the adjoints. Now, why do we care about the orders? Because generally, the operators don't commute. So, composition of operators satisfy a few properties. Firstly, we do have associativity. It's easy to see by just sequential mapping that we can, if we have a set of operators, it doesn't matter the order in which we multiply them, that's equal. However, commutivity is not necessarily the case. So generally, the composition of A times B does not equal the composition of B times A. They don't commute generally. That is to say, AB is equal to BA plus a remaining piece that we call the commutator. Where the commutator, as you know, plays an important role in the mathematics we use in mechanics. It's just the difference between the operators in the two different orders. All right, so what are some of the properties of the commutator? Well, firstly, you can see immediately that it's anti-symmetric. That is to say, if I take the commutator in the other order, it's not the same, but there's a minus sign. It's linear in the following sense. If I commute A, or either way, it doesn't matter, some linear combination of operators, with scalars, that's the same thing as a linear combination of the commutators. Another important rule that is important to get used to, we use it all the time, is the product rule for commutators, which you can check for yourself quickly. So if I have the commutator of A with the product of two operators, then what I do is bring that guy out and commute A with C and multiply that, or bring this guy out. But be careful, you got to put it in the right order, because generally they don't commute. Alrighty. Conjugation. If I look at the operator I get by commuting A with B and I conjugate that, well, I conjugate each piece here, right? And that, of course, switches the order. That becomes B dagger A, that becomes, B dagger A dagger, this becomes A dagger B dagger, and this thus is equal to, because I reverse the order, minus, right? Now, one thing we can say thus is that if A and B is Hermitian, A and B are Hermitian operators, then the commutator between them is anti-Hermitian. Right? Because these guys are Hermitian, that means the dagger of the commutator is minus the commutator. You know that. If you have X and P, their commutator is IH bar. Right? Okay. And finally, there's one other property, which is, which you can read. It's not even, we never use it anymore for other things, but there's a Jacobi identity. It's a property that it makes this a Lie bracket that is sometimes in more dense stuff. If I look at the commutator of A with the commutator B and C, and then I cyclically permute it all through, commutator of C with A and B plus the commutator of B with C with A, that all adds up to 0. Not such an important property, but one I'll just note. All right. One quick note. We sometimes talk about the anti-commutator, which is not universally, but often written instead of with a square bracket, a curly bracket. And it's defined A times B plus B times A. Instead of with the minus sign, it's got the plus sign. Okay? And the reason it's called the anti-commutator is what it says is that A plus B then is equal to minus B with A plus the anti-commutator. So it says when you reverse the order, you put a minus sign and then add the anti-commutator. Whereas with the commutator, I just reverse the order. And the anti-commutator is, as we'll see next semester, important in the theory of fermions. I never know whether fermions has to be capitalized. I mean, it's Fermi after all, but I'll go back and forth. All right, very good. So let's go back to our example over here about Pauli operators. And let's look at the commutation relations and anti-commutation relations of the Pauli operators. So, as you mentioned, Zeke, there's the relationship between, so if I define, remember, the Pauli operators that we call, let me label them I equals 1, 2, 3, or X, Y, Z, is the spin component divided by h bar over 2. Okay? So this is spin angular momentum. And we recall that the components of spin angular momentum satisfy the following commutation relations. This I is not the same thing as that I, that's the actual square root of minus 1. With the times h bar. Sorry. This is the Levi-Civita symbol, the completely symmetric tensor, and I'm using the Einstein summation convention, where repeated indices are summed over. Okay? So, what that tells me is that the commutation relation between two Pauli matrices, if I divide everything by, or multiply everything by h bar over 2, divide all these guys by h bar over 2, this is 2I epsilon I jk. Okay. Okay, that's where the 2 is. So let's check that. We got our vectors over here, or I'm sorry, our Pauli operators over there. So sigma x times sigma y. Let's do it in terms of matrices, because it's easier, I think, to multiply matrices, 2 by 2 matrices together than deal with all the pros and cons. So sigma x times sigma y is that matrix multiplication. And that is equal to what?
0, 0, 1.
I 0, 0, minus I. Right? And sigma y times sigma x is equal to minus I, 0, 0, plus I. So that tells me then that the commutator of these two is equal in this representation to this minus that, which is equal to 2I, 1 minus 1, 0, 0. Which is equal to 2I sigma z. Yay! That's me just a little bit ahead. Okay. So that works pretty good. There's another property, though, that's interesting, and this perhaps even was what we're thinking about. But the anti-commutator of the Pauli matrices is, there's no two here. That, this is time to get in. It's going to be 2. Yeah. Right? Because, so for example, what's the anti-commutator of sigma x with itself? 2, right? Because this is sigma x times sigma x plus sigma x times sigma x, and each Pauli matrix squares to 1. So this is 2 times unity. The anti-commutator of sigma x and sigma y, that's to say, for if I isn't j, this should be 0. Is it? Well, that's sigma x times sigma y plus sigma y times sigma x. We just did that. Add these two together, you get the 0 matrix. So, Pauli matrices, different Pauli matrices anti-commute. Okay? That's an interesting property. Pauli matrices have all kinds of fun properties which we'll use throughout the year. All right. Very good. So, now the next thing we want to talk about, be the most important thing, the lecture really, is to remind ourselves about the theory of eigenvectors and eigenvalues. So, generally, we said we have a linear operator. It maps some vector to some other vector. Okay? However, there is a special, there are what are called characteristic vectors. Or, because this was done in Austria and Germany first, eigenvectors. So eigen means characteristic. of the map, which are such that if I operate this, one of these vectors labeled by a number lambda, if I map it by m, the act of the map is just to scale the vector by that number. Okay? Such vectors are called eigenvectors or characteristic vectors of the map or operator. And the scale factor for that particular vector is the characteristic value or the eigenvalue. Okay. So, by that, we're not talking about, we ignore the trivial case. Where this is just the zero vector, I'll call it null. That's to say, the column vector with all zeros in it, that's always an eigenvector, because multiply that 0 times, then you get that 0. Okay, so the eigenvalue can be 0, as we'll see. But the case where this is the 0 vector, we're not including that. That's a trivial case we're ignoring that. Okay, this is the vector. What I mean by this is all zeros. No basis. That's the null vector. So we ignore that. That's obviously always an eigenvector. Another thing to note is that if this is an eigenvector, with eigenvalue lambda, then I can scale that vector by any scalar. And this is also an eigenvector with the same eigenvalue. But again, they're not considered as distinct. They're really a whole ray. The whole ray in Hilbert space is the same eigenvector. This is not a distinct eigenvector from this. It's just scaled. So typically, we will, at least to some degree, specify the eigenvector by specifying the length of the vector. It's still not completely defined, because I can multiply it by a number which has magnitude 1, that's to say a phase, but what phase we choose will be a matter of convention. So typically, we fix the normalization, or the length, such that it's a unit vector. That doesn't yet, as I say, completely specify the eigenvector, because I can multiply it by a phase, and it would still have norm 1. All right. So, now, there is a theorem which I'm not going to prove, which states the following. Oh, I guess before I get to that, I wanted to show you that. So let me do that first. So let's just let's just consider a rotation in three-dimensional real space about the z-axis. Okay, so my Hilbert space here is a real three-dimensional Hilbert space. That's fine. I can do that. can expand it to complex. So I'll have an operator, which is a rotation about the z-axis by some angle theta. So here's the z-axis. Here's the xy plane. I shouldn't put hats on these guys. I can call them hats, what the heck. And I'm rotating about the
It's
z-axis.
Z twice.
There's a y there. Someone's paying attention. And I rotate this by some angle theta, okay? So, the action of my operator on the x basis vector is this basis vector, which has cosine theta along x and sine theta along y. Okay? The action of this rotation operator on the y basis vector is minus sine theta on the x and cos theta on the y. And the action of this on the z is to do nothing. Leave the z-axis alone. Okay. So now I ask you, what is the representation of this operator in this basis?
Cosine theta, sine theta 0, minus sine theta, cosine theta 0, 0, 0, 1.
Right, in some order. So how do I do it? The way what I want to emphasize here is one of the points I made at the very beginning of the lecture. I can immediately write down, without doing all the bras and cats, although I could write down the bras and cats, it's kind of up to you, how you feel comfortable. If I know how the operator acts on each of the basis vectors, then I just have to write down that image as a column. So this is cos theta, sine theta, 0. That is the representation of the operator acting on the first guy. Minus sine theta, cos theta, 0. That is the representation of this guy as a column vector. 0, 0, 1. Okay. Again, you could do the bras and cats. You'd get the same thing, right? Row, column, row, column. All right. All right. So, what was I going to say? Oh, yeah. So this is the rotation matrix. We can see immediately here that this guy, that this is an eigenvector. And what's the eigenvalue? +1. So that geometrically what you see is the operation of this map on this basis vector, on this eigenvector, was to not change its direction. It left it alone. That's what an eigenvector must do. But in addition, in particular, it doesn't just not change its direction. In this case, it left its magnitude the same. So that's why the eigenvalue is plus 1. Okay? All right, so now to the theorem. So how do we generally find all the eigenvectors and eigenvalues of the operator or the matrix? Well, now I want to just invoke a mathematical theorem which says the following. Okay? An operator on a finite dimensional Hilbert space has a dimensional Hilbert space of dimension d, has d orthonormal eigenvectors if and only if M commutes with its adjoint. Such operators are known to be, if they satisfy this property, that they commute with their adjoint, they're called normal operators. A normal operator is one that commutes with its adjoint. Now, our favorite operators in quantum mechanics are normal operators, right? So, for example, a Hermitian operator are normal operators, right? Because if it's Hermitian, M is equal to M dagger, and everything commutes with itself, right? So that's cool. But also unitary operators are normal operators. Why do we know that? Well, we know that U dagger U is 1, and U dagger, although I've written, is also 1. Right? So the commutator of U with its adjoint is 0. U commutes with its adjoint. It's not equal to its adjoint, generally, but it commutes with it. So what that means is that both Hermitian matrices and unitary matrices, or unitary operators and Hermitian operators, have if they act on a d-dimensional Hilbert space, there exists d orthonormal eigenvectors of those operators. That's not true of all operators, but it's true if they're normal. And if they're normal, then it's true. Okay? All right, so what can we say in this case? Well, the rotation operator that we're just talking about right here is unitary. It's actually orthogonal in this case, but orthogonal matrices are also unitary matrices. How do we see that? Well, the inverse of this operator is just rotating in the other direction. Right? This is one way to look at it. So if I look at this with the minus sign in it, that's cos of minus theta is theta, but sine is minus sine. But that's just the transpose of the matrix. But since it's, all the elements are real, that's also the same thing as that, because everything is real. So this is the same thing as that. So this is unitary. It's also orthogonal. An orthogonal matrix is one whose inverse is its transpose. But if there's always a real matrix, then it doesn't really matter. We call it unitary. So this matrix, or this operator, has three orthogonal eigenvectors and eigenvalues. Now, what are the other eigenvectors of R? Kind of hard to imagine that, isn't it? I mean, what we said is that the property of the eigenvector is such that when you map it, it stays in the same direction. Yeah?
They're complex.
They have to be complex in some way. So let's see what they are. You'll recognize them.
They sound complex.
Sorry? Think about that. Yeah.
No, we were saying that they sound complex. Pun
Oh.
intended.
Like the eigenvalues, even plus or minus.
Yeah, let's do it out. Let's do it out. So let's remind ourselves how we find eigenvectors and eigenvalues of a matrix. Okay? So the defining equation is written over here. Generally, an eigenvector satisfies that it stays the same up to multiplication by the eigenvalue. Which means that this combination acting on this gives me the null vector. Okay? And since we are ruling out the null vector here as an eigenvector, that means that this thing cannot be invertible. Because if it was, then this would equal 0. And it doesn't. And since it doesn't equal 0, I mean, since this is a singular operator, singular matrix, that means that the matrix has determinant 0. So we find the eigenvalues by what's known as the characteristic equation, or the eigenequation. Which says that the determinant of the matrix or operator minus lambda times the identity is 0. Okay. All right, so this object is called the characteristic polynomial. And for a d-dimensional Hilbert space, it has d roots. And those d roots are the eigenvalues. Now we could say a few things, just in terms of definition. If eigenvalues are the same, or if any two eigenvalues are the same, they are said to be degenerate. And the corresponding eigenvectors are said to be degenerate. So we have degenerate eigenvalues and degenerate eigenvectors. Okay, we'll get to that soon. What are the nature of the eigenvalues? Well, it depends on the roots here, okay? So if this characteristic polynomial is real, it's a real polynomial, which doesn't have to be, because we might be looking at unitary matrices. Then what can you tell me about the roots? The roots of a real polynomial. Not always, but if they're complex, they come in complex pairs, right? So if the polynomial is real, like, you know, if you have x squared plus 1 is 0, then the roots are plus or minus I, right? So if the polynomial is real, that means that if any root or any eigenvalue is complex, then the conjugate is also an eigenvalue. All right, let's take a look then at our specific example of the, oh boy, high five and you're having kind of fun. The roots of our characteristic polynomial for this matrix. Okay, so let's write this down. Let's write down the characteristic equation. The determinant of cos theta minus lambda sine theta 0 minus sine theta cos theta minus lambda 0, 0, 0, 1 minus lambda. That determinant has to equal 0. So you take the determinant of that matrix, you got cos theta minus lambda squared minus sine squared theta all times 1 minus lambda.
Plus sine squared, if it's minus that.
It's plus, yeah. Thank you. Okay. So we have the roots. 1 minus lambda is 0. There's one root, which is lambda is 1. And then the other roots are the roots of this quadratic. And I'll leave it to you to quickly show that the roots of those are e to the plus or minus I theta.
Cosine squared plus sine squared terms just equal 1.
It does. But then you have the cross term. You have to equal to set this equal to 0. these are the eigenvalues. Now, I'm running out of time, so I'll finish this up next time. I just want to say one last thing. What are the eigenvectors? We'll remind ourselves how to find them, but let me just write this out because I think it's kind of neat just to remind you. So, the eigenvectors are the following. That is to say, if I act this rotation operator on this vector, this is e minus plus. So this on e plus or minus is e to the minus plus. These vectors you recognize, maybe. As the vectors we talked about in electromagnetism, they were related to circular polarization. Plus and minus helicity circular polarization are the eigenstates of rotation about that axis, with eigenvalues representing the phase of the rotation. This basis, this complex basis, will play a very important role next semester. This is sometimes known as the spherical basis. Not to do with spherical coordinates, but it has to do with spherical symmetry. It's the basis that will play a very important role in the theory of irreducible tensor operators and the Wigner-Eckart theorem and all this good stuff that we'll see next semester. But anyway, it is a basis, and is it orthonormal? Yeah, we showed that these guys are orthogonal, they're obviously orthogonal to Z. All right, I will post the notes, and you'll see the remaining stuff, especially something we need for homework. So I'm sure we can address that. All right.